Today, we want to talk about complex roots. Remember that we introduced the idea of complex numbers last time? Remember, we only need those 4 powers of I, and they all equal plus or minus 1 or plus or minus I. So remember the 4 powers that we need. I is just I. Then I squared is -1. I cubed is -I, and I to the 4th is equal to 1. So if I have some big power of I, because I multiplied a bunch of polynomials that all have I in them, and I have an I to the 7th. I know that I to the 7th, we can take out a bunch of I to the 4ths. 7 minus 4, we can subtract 4 one time, that'll leave us with 3. So I to the 7th is the same as I to the 3rd, which is just -1. What we're looking for is the remainder upon division by 4. So if I have I to the 215th, take the 250, that would be an awful thing. I hope I didn't put that on the final. We have to multiply a polynomial, because that's like I to the 215th power that you have to simplify down. But anyway, we just take the 215, divide by 4, and the remainder will be a 0, 1, 2, or 3. Because those are the 4 possibilities when we divide by 4. The remainder could be 0, 1, 2, or 3. Really, when we look at I to the 215, 200 is divisible by 4. So that's going to be the same as I to the 15. Then we subtract, take 15, divide that by 4. We can do that 3 times with 3 left over. So I to the 215th is the same as I to the 3rd. So it's -I. Here's the thing that we want to look at today. We want to consider square roots, cube roots, 4th roots, 5th roots, and in general, we say nth roots. We got to do a quick algebra catch-up. When I write these radicals, this is using radical notation. That's a little bit self-aggrandizing. I mean, it's cool and all, but I wouldn't call it radical, but I don't know. It's like giving yourself your own nickname. You just can't do that, right? You can't write a notation. It's like, oh, this notation is radical. It's like, oh, nah, it's all right. But I wasn't at that meeting. So I was like, oh, why don't we just put all right notation? Actually, I wouldn't have said that either. I would have said, let's ditch this and just use fraction exponents. And they'd be like, oh, we can't do fraction exponents. We got to do this. It's radical. Anyway. This radical notation can also be written with fraction exponents. So we can write it with exponents, so fraction exponents, or radicals. They mean the same thing. The way to convert from one to the other is that the index of the radical is the denominator of the exponent. The index of the radical is the denominator of an exponent. The generic radical all by itself with no apparent index, that index is 2. This is one of those cases where the default isn't a 1, the default is a 2. So the radical symbol all by itself, the index of that radical is a 2. That's our square roots. So for our second roots and our third roots, we have special names. We have square roots for second roots, and we call third roots, cube roots. After that, we stop giving them names. Then they're just 4th roots, 5th roots, 6th roots, and so on. I don't know, those 2 are special. This would be a messed up thing to do if you have more than 3 kids. My first kid is like, this is square, then cube, 4th, 5th, 5th. Like, remember your kids. That would be really messed up. Especially if like those first couple of kids have like middle names as well. And then from there on out, it's just like all 4th, 5th, 6th. Then you can go full Roman calendar style. And this is my kid, sixth leech. Oh, is he your sixth kid? No. He's my fourth kid. I thought, just like December with the deck for a 10 with the 12th month, just to mess with people. I don't know how Rome was so friggin' successful with such a crappy number system. That makes any sense. Anyway, what are we talking about? Yeah. The index of the radical is the denominator of the exponents. Let's get to the big idea. Let's just go right to the big idea. Let's jump straight to our conclusion. Every number has nth roots. Every number has nth roots. All numbers have 2 square roots, 3 cube roots, 4 fourth roots, 5 fifth roots, but we have to allow complex numbers. And right now you're like, oh, dude, you should have told me that you were going to insert an entire word between n and n. So every number has n complex nth roots. There's always 2 square roots. There's always 3 cube roots. There's always 4 fourth roots. And so on. We do have to allow complex numbers to be our roots. So for example, we're going to translate this into an equation. So we're going to read this as the equation x to the n equals some constant always has n complex solution. This is how we're going to interpret this. Every number has n complex nth roots. So the equation x to the n equals some constant must have n complex solutions. So it's going to start off very algebra, and then we're going to drop some trig into it. Let's start with this one. The x squared equals 1. Now remember, I'm not asking what is the square root of 1, because then we would just say 1. We're saying, what are all the square roots of 1? What is every number such that when you square it, you end up with 1? And here we know there are 2 solutions. We know this in 2 different ways. We might think that x equals plus or minus the square root of 1, which is plus or minus 1. There are our 2 solutions. because here we're thinking of doing inverse operations to each side. We could also see this in terms of polynomials. Whichever way we think about it, we end up with those two solutions, plus or minus 1. It was an nth degree polynomial equation. We found two solutions. We know we got them all. Here's where we're going to find some, we're going to get into some problems. So we got x cubed equals 1. Our current set of techniques, our current skill set will allow us to find the one real solution, but we need something that'll find us the complex solutions as well. We know there have to be 3 solutions. If all we do is do the inverse operation to both sides, or inverse operations in reverse orders, then x is the cube roots of 1, which is just 1. This is the real solution. Here's the one real solution, but there have to be 2 others because we have to have 3. We have found 1. There are more. To help us deal with this, we're going to think in terms of algebra and polynomials. I'm going to do the same thing that I did in the previous problem. I'm going to take my x squared equals 1, and I'll subtract 1 from both sides to make a polynomial. Then we can factor. So I'm going to rewrite this as x cubed minus 1 equals 0. And then I'm going to factor using the difference of cubes. Everybody remembers difference of cubes, right? There's not a quiz today on difference of cubes. So you can just be like, oh, yeah, totally. Absolutely. And I'm not about to say, what is it? I'm just gonna write it down. The difference of cubes looks like this. First of all, if you remember a little bit about the form, you know that one of the factors of x cubed minus 1 has to be x minus 1. We know for a fact that one of the factors of x cubed minus 1 is x minus 1. Because I know that one of the zeros, or one of the solutions to this equation is 1. If 1 is a solution of the equation, that is 1 is a 0 of the polynomial x cubed minus 1, then x minus 1 has to be a factor of the polynomial x minus 1, or x cubed minus 1. We happen to remember, I'm saying oops, I spelled 2 wrong though. We all happen to remember the difference of cubes formula, right? We're all pretending that at least. So we knew we were going to get this factor of x minus 1 because that is going to give us the solution, the real solution, x equals 1. We had a real solution already, so we definitely knew that this is one of the factors. We happen to remember our difference of cubes formula, so we were able to just write down what the other factor was. Note that our other factor is a quadratic, that it's not factorable, so we can use the quadratic formula or completing the square to solve, to find the solutions that come from that factor. For this x squared plus x plus 1, we could either complete the square or use the quadratic formula to find the solutions over here. Once we start completing the square, half of the coefficient of x is 1/2. 1/2 squared is 1/4. I need a 1/4 to complete the square. I'm breaking up the +1 into a 1/4 plus 3/4. So I'm just splitting up the 1. I'm pulling off the 1 what I need to complete the square. And then that leaves a 3/4 behind. Now we can solve by doing inverse operations to in reverse order. Inverse operations in reverse order. So it'll look like subtract the 3/4, then the square root, and then subtract the 1/2. When we undo the square, we take a square root of both sides. Oops. Forgot the negative. First subtract 3/4, then take the square root of both sides with the plus or minus, then subtract 1/2 from both sides. Now over here, I've got the square root of -3/4. We expected this to happen. We knew this was going to happen because we knew that there were 3 complex solutions. Inverse operations just on the original gave us 1 for a real solution. That leaves 2. And here are our 2 complex solutions. Some more fun stuff. I don't know if fun is the right word, but I'm going to use it anyway. Some more fun stuff about these solutions. Complex solutions to polynomial equations with real coefficients always come in conjugate pairs, A plus or minus BI. So complex solutions. Complex solutions to polynomial equations always come Complex solutions to polynomial equations with real coefficients always come in conjugate pairs. How's everybody okay? No, far from okay. Because you're like, oh, am I going to have to do algebra on this trig final? And I'm like, oh, no, this is all just to get at this 1/2, the -1/2, and the plus or minus √3/2. Two numbers that should definitely cause you to notice. I got a -1/2 and I got a plus or minus √3/2. I got a 1/2 and a √3/2. Am I talking about 30 degrees or am I talking about 60 degrees? The answer is yes. I must be dealing with a 30 or a 60. If there's a sign and that 1/2, that's going to give me a 30. But the sign of the √3/2, that's going to be a 60, right? 1/2, especially when we pair it with a √3/2, should start making you think about 60 degree or 30 degree reference angle. Any questions? Fun fact, let's pretend that we did not remember the difference of cubes formula. At that point, we would have to use our knowledge that x minus 1 is one of the factors, because we know that x equals 1 is one of the solutions. Then at that point, we can divide. Since we know that x minus 1 has to be a factor, if we took x cubed minus 1 and divided by x minus 1, that would give us x squared plus x plus 1. If we didn't remember the difference of cubes, then we could divide the x cubed minus 1 by x minus 1 because we know that x minus 1 is a factor. We know that because we know that x equals 1 is a solution. Well, I should say 0 of x cubed minus 1. There are other ways that we could find this out. Like we could ask a machine for it. Incidentally, I had graphed this earlier because this is the equation to make a heart. So, but if we had a much more boring equation, x cubed minus 1, or more boring function. There's an alternate form, x minus 1, x squared plus x plus 1. So here would be the other way that we remember. There's our real root at x equals 1, and there are complex roots, -1/2 plus and minus √3/2 times I. You should know that if you're using some kind of machine to solve your problems and write your answers down, it's super obvious when you're doing that. Because you would write your complex zeros like this. This is following the instructions, but notice that I changed it up because when I had the square root of 3/2, since that was a whole fraction, I did put the I on the other side instead of including it in front of the radical. And you were like, and no one called me on it, which is, I don't know, typical. No one ever does. You think I'm just doing some kind of weirdness. The reason that I put the I after the radical, even though last week I'm like, oh, don't do that, people will get confused, is because the radical, the square root of 3, was as part of a fraction. And it's really easy to make sure that that fraction is separate from the I by making sure that the fraction bar is pointed right at the I. That sounds way more threatening than it should be. The fraction bar will be pointed right at your I. Any questions? That was too much algebra for a trig class. No one's happy right now. That's okay. There's no class on Thursday, so I feel better about it. Okay, so let's put that aside. We found our 3 complex zeros of 1. 1 was our real 0. Remember, real numbers are also complex. And we also had these 2 other ones, -1/2 plus or minus √3/2 times I. That's -1/2 plus √3/2I and -1/2 minus √3/2I. Really. X to the 4th equals 1. In this case, we know that there are 4 complex solutions. We might be able to easily pick them out, plus or minus 1, plus or minus I. If we do the inverse operations in reverse order, that's going to get us our real solutions. Since we're undoing an even exponent, and even exponents don't respect negatives, we have to do a plus or minus. Here are 2 real solutions. Which means there are 2 more. Let's come at this from a polynomial standpoint. If we come at this from a polynomial standpoint, subtract 1 from both sides, have x to the 4th minus 1 equals 0, I can start to try to look at this polynomial as a product, and then I could make each of the factors equal to 0. Since x to the 4th is even, I can say x to the 4th minus 1 is x squared minus 1 times x squared plus 1, using the difference of squares. At this point, I can use the difference of squares again. X squared minus 1 can also be factored. X minus 1 times x plus 1. And then we still got this x squared plus 1 to deal with. Here are the 2 real solutions. And here's where we're going to get our 2 complex solutions. So if we take the x squared minus 1, or sorry, x squared plus 1 equals 0, if we apply inverse operations in reverse order, there are the other 2 complex solutions. So the 4 solutions to x to the 4th equal 1. plus or minus 1, and plus or minus I. Once we got down to x squared plus 1 equals 0, and I just did inverse operations in reverse order, that is, take the square root of both sides, I knew we were going to be okay because we were expecting 2 solutions from the x to squared plus 1. A second degree polynomial equation will have 2 solutions. We had to do more than this plus or minus 1 from the x to the 4th equals 1, because now that we're allowing complex solutions, I've got to have 4. My first attempt only gave us 2 plus and minus 1. So there's 2 other ones. We had to find them. How's everybody okay? Now we need to connect this to trigonometry. We're going to connect these solutions to these algebraic problems in trigonometry by plotting the solutions on the complex plane. So the complex plane just has 2 axes, a real axis, and an imaginary axis. I know it looks like an X and Y axis. It's totally not an X and Y axis. Totally not. It's a real axis and an imaginary axis. See how different it is? It's not. It's a 2-dimensional. We're just going to have 2-dimensional things. It's just numbers will have 2 parts to it. So what we're going to do is we're going to plot numbers, complex numbers, a plus bi. So here's the number a plus bi, and it's going to have an a real coordinate of a, and the imaginary coordinate is b. That's all. It's got 2 parts, so the natural thing to do is to make 2 axes. You've got 2 parts. The natural thing to do is make 1 horizontal and 1 vertical. Like if you're rolling 2 dice and adding up the totals, it makes sense to just write 1, 2, 3, 4, 5, 6 horizontally, and then 1, 2, 3, 4, 5, 6 vertically. Just make it 2-dimensional. If you're rolling 3 dice, then you just have a third one, 1, 2, 3, 4, 5, 6 in a 3rd dimension. If you have 4 dice, well, you need a 4th dimension. It gets a little bit messy. It's really hard to picture things in 4 dimensions, especially if we're going to draw it. But right now, we just got 2. The square roots of 1 were both 1 and negative 1. So on our complex plane, they both show up on the real axis. Here's plus 1, 1 plus 0i, and then negative 1. plus 0i. The square roots of -1 were plus or minus I. So I'm going to plot those on our complex plane. Zero plus I and 0 minus I. Then we're going to draw the fourth roots. I'm going to skip the cube roots for a second. And we're going to draw the fourth roots. Because it's just a combination of the previous one. Makes sense. -1 squared is +1. So the fourth roots of 1 are the square roots of 1 and the square roots of -1. So that's why we get these 4. Now we want to draw a picture of the 3 cube roots of 1. The real one is 1, and then there's 2 complex ones. -1/2 plus and minus the square root of 3/2 times I. I can only reliably draw 1/4 of a circle. Like the second quadrant, I can draw. That's always the best one. The other ones are all just messed up. And what I should be doing is drawing this one and then like rotating the entire paper so I could draw the other ones, but I never do that. I don't know why. So here are our 3 cube roots of 1. There's 1 plus 0i, that's this one here. Then I've got -1/2 plus √3/2. And down here, I've got -1/2 minus √3/2i. What we want to notice about these 3 cube roots of 1 is what we noticed about that the 1/2 and the √3/2, and why I put this all sitting on a circle. Note that if we look at this -1/2 and √3/2, over here in the second quadrant, it's the cosine that has the cosine of an angle that's negative, and the sine of the angle is positive. Also, the horizontal component is cosine and the vertical component is sine. So this is sitting at a reference angle of pi/3 radians, or 60 degrees. Which means this is sitting at a 120-degree angle. And I'm going to use degrees because it's going to be easier to divide by 3. And then this -1/2 minus √3/2, we're using the same values. So that's going to be a 60-degree reference angle. And so that is 60-degree reference angle in quadrant 2 and a 60-degree reference angle in quadrant 3. So these two zeros, these two roots of 1 are 120 degrees apart. If I've started from the first one and took 120 degrees to get to the first one, then another 120 degrees to get the second one, it's going to be 120 degrees to get back to the start. What we discover is that the cube roots of a number, once we plot them on the complex plane, will always be 120 degrees apart. They'll be evenly spaced around the circle. Since the circle is all 360 degrees, if we need to put three things there, 120 degrees apart. If we need to put 2 things there, 180 degrees apart. If we need to put 4 of them, 90 degrees apart. But they always evenly space. So we didn't go and find the 5th roots of 1, but we would just take the 360 divided by 5. Those roots would be 72 degrees apart around that unit circle. That's how you know where to put the pistons in a 5-cylinder engine. They have to be 72 degrees apart. Not the pistons themselves, but what's the part that moves the pistons? Crankshaft? Crankshaft. Anyway, 72 degrees apart. Everybody's like, all that's going away. They'll all be electric cars pretty soon. How's everybody okay? Electric cars are going to be one of those things. Right now, most people drive like gas cars. Because like think about like electric cars in 2012, 2013. Like the only one that was selling in volume was the Tesla Model S, which was pretty expensive. So it's like if you're driving around in a Model S, you're like, oh, look at the fancy person driving around in a Model S. Electric cars, fancy. Gas cars, whole range, right? But then other manufacturers are like, oh, well, shoot. Apparently, we are not successfully able to stop electric cars from showing up. So now we're going to actually have to do work. That's really the reason, the thing that stopped electric cars. Shit, we're going to have to do some work now. GM actually did this in the 90s. GM made an electric vehicle in the 90s. Look up the EV1. Then they killed it because they're like, oh, whoa, this is going to cut into our gasoline sales. And the oil companies are like, well, what? Gasoline sales will be affected? Can't do that. You know what I mean? But then electric cars, manufacturers are like, oh, what if we tried to sell an electric car to just like anybody? Let's make a reasonable one. Unfortunately, they made things like the Nissan Leaf, which was an electric car, had a good range. But have you seen one? They're weird. They're like, well, it's an electric car, so it's got to look all weird for some reason. Like, well, just make it look like a fucking car and just have it be electric. And now they're finally doing that. Let's see. Despite the fact that Teslas all look the same, they are still a little bit weird looking, right? But now Mercedes has like their small crossover, there's a little small boxy SUV. They have an electric version of that, and it just looks like the regular gas one. They still have the weird sedan. I'm like, oh, let's make an egg-shaped sedan. I mean, it looks like a melted pudding. So if you really want the electric car to be like stupid looking, you can go with that. But if you just want a car that happens to be electric, you can actually get one. Here's how you could tell the real electric car revolution is coming. Ford made an electric F-150. Ford's like, oh, you want to sell electric cars? We'll make the F-150 electric. Done. That's the indication. That's what's going to make that. That's what's going to I think, in my opinion, lead to the infrastructure. Because everybody buys F-150. You know what I mean? I think GMC went too far with their weird looking Hummer. I think it's a little bit too futuristic. Stop making it look like weird shit. Just make it look like a regular car. And people will buy it. Like right now, if I gave you $100,000 and told you to go buy an F-150, do you think you could do it? No, because they've all been sold. Because like, oh, what's that? A normal looking vehicle? Yeah, I'll take that. You know what I mean? Don't stop making it weird. Still doesn't address the problem, by the way, because we're still going to be driving all individual cars. So eventually we're going to discover that that was the problem all along. Cars, everybody having their own car, that was the problem all along. It's a cascade failure too. Like, oh, but I have an hour-long commute every morning. That is also a problem. That we set up a society where certain members of our society were like, oh, we have to drive for an hour to get to work, or an hour and a half, or 2 hours. What the fuck is wrong with us? Now we would take someone and say, you know what? We know that you're working 8 hours, but we're going to extend that by half. We're going to make you do another 4 hours and we're not going to pay you. This is if you want to, I don't know, live in a building. All right. All right. So this is the cool parts. I know it doesn't seem that cool, but this is the cool part. When you have nth roots of a number, they're always going to be evenly spaced around the complex plane. Cube roots, there's always going to be 3 of them. They're always going to be 120 degrees apart. If we did the cube roots of -1, we know one of the real roots is -1. That's over here. These other 2 just get moved over. We just take this whole thing and rotate it 180 degrees. So we know what the other 2 are. We wouldn't have to do any work. All right. Also, if I ask for the 4th roots, for example, If I wanted the fourth roots of, let's say, 1/2 plus root 3 over 2i, I would just take these four, and rotate one of them to sit at 1/2 root 3 over 2. And then the other ones would be 90 degrees off of that. So we could just figure out geometrically where the other 3 roots are. We wouldn't have to do any algebra at all. Is everybody okay? All right, so that's going to do it for today. That's the thing about complex roots. What happens now is that I post a few more quizzes. Make sure we've covered all our bases. That will be our final exam. The final exam is just going to go on Canvas. We don't have to come in and meet for a final exam because we're trying to be modern and move forward and be convenient. So check for problems that are showing up on Canvas. Anything that is a homework problem, that stuff is due on December 9th. On December 10th, homework problems will no longer be available. They won't even show up. You'll click on them, and it's just be gone. It'll just be like, if I could make it just to have a big no on your screen, that's what would happen, but it's just not going to be available. But you knew this at the beginning of the semester. So you're going to be like, well, can I have an extension? I missed 40 assignments. Can I make those up over the weekend? It's just the answer is going to be no. Any problems that show up, any new quiz problems, those are going to be due the following week. That's the end of finals week. December 9th is the end of the semester. December 16th is the end of finals week. That will be when everything is due. Anything else is due. That make sense? If you email me on December 17th asking for an extension, you're not going to get a response until January when I come back and open up email again. Obviously, that's an exaggeration. I am going to be checking for emergencies. What you need to do is check on your grandparents and make sure your tires are well inflated. That's the kind of shit that's going to happen now. It's finals week coming up. Very dangerous time to be a tire or a grandma. You know what I mean? Know that if you come at me with that, I know that you're lying. And you're just taking your chances. If I'm like, oh, that's terrible. Here, I'll give you an extension. Don't think that you got away with anything. Does that make sense? I always know when you're lying. It is super obvious. Like, oh, did you get this answer from a computer? It's like, oh, no, I did that by hand. And then in your mind, you're like, oh, please don't say show me. Please don't say show me. Please don't say show me. Because you wrote it just like Wolfram Alpha would. Oh, what a coincidence. I guess I'm as smart as Wolfram Alpha. I got to go. Bye. You know what I mean? So anyway, that's going to do it for today. That's going to do it for this week because of Thanksgiving. So everybody have a nice Thanksgiving weekend. I will see y'all on Tuesday. Thanks for playing.